So now that we know how to measure torque and angular velocity, we need to put this all together. So I'm going to show you approximately what I built 2 years ago. This is the original crank off my bike. I used my tax refund about 3 years ago to buy a SRAM Rival group set. And I pulled off my old group set and it contained this FSA Vero crank, which is a 3-piece crank. And at the time, my university master's degree that I was working on involved some experimental work, and one of the things we were investigating was building a tiny load cell. So as such, I had access to some strain gauges. And you can't really see them, but these were applied in a very crude way. I sanded the crank and I applied a linear gauge at the top and the bottom to make up those 2 legs of my Wheatstone bridge that I mentioned earlier. The other 2 resistors were just going to be 120 ohm dummy resistors. You can also see that I have this wire, I believe, taken from a network cable, and it's all covered in epoxy, some 5-minute grade epoxy. This proved a concept to me that this is a viable way of measuring it. What I found, though, very disheartening at the time, approximately 3 years ago, was that it was very noisy, it was drifting significantly, it was not well behaved, there was huge levels of RF interference. So I shelved the project until I completed my master's degree, and then I moved on to getting a real job. And then partway into my real job, I got to put up my hand and said, hey, you guys want to do some experimental stuff? Well, let me do it. I have had experience with this. The stuff that I was building, I knew the application process, I knew the circuitry. What I didn't have was the fine details, and sure enough, they said, all right, great, Keith, we'll ship you off to North Carolina to the Shea and get you all trained up. And I learned a lot of valuable elements there. And part of the big thing that I learned is precision resistors. You can't grab 5% off the shelf resistors to complete a Wheatstone bridge. You can't do that. You need 0.1, 0.01% resistors. They need to be ultra low thermal drift. We're talking less than 5 ppm, which is a measure of parts per million of ohm per degree. So once you do that, everything stabilizes. And I moved on and I expanded the concept with new gauges on my OEM SRAM Rival crank. I used a double bending bridge arrangement rather than the single bending bridge, so doubling the sensitivity. And I did the exact same on the other crank arm. But I also investigated installing some shear gauges on the outside of this arm. And I also investigated putting a gauge inside this crank tube. And both of those experiments kind of worked, but what ended up being put on the bike and in a video that you can find was using the top and the bottom bending bridge arrangements. They work exceedingly well. They are highly isolated. They are highly repeatable, but they're not placed well. And you also have to run wires through the crank. It's something that an average person can't do. However, a new design simplifies the matter. As you can see, the very fine wires running out from the sensor inside, which is 4 strain gauges on the one grid, taking 6 wires that run back to the circuit board. And this circuit board is actually an evolution of a very, very small circuit board, which just contains an instrumentation amplifier and an analog to digital converter. This board takes that circuitry and puts it here, and then adds an Arduino Pro Micro. It's very hard to see, but inside here is also another shear gauge, like I explained at the whiteboard, like I attempted on the outside here. Inside, it's much more protected. It's behind the crank ring, so, and in an area that the crank rings essentially protect it, and the chain can't get access to it. And these are all covered in a polyurethane coating. So one of the things that I actually did for this is I bought proper, you can see right on the side, the Micro Measurements logo from Vishay. In Canada, the reseller is Intertechnology. These guys know their stuff. They are very, very, very willing to help out. I've used these guys at work, and I've used them for my own personal projects. If you're in Canada, if you're in Ontario especially, and you need some strain gauge supplies, give these guys a call. They're selling top shelf stuff, so this isn't cheap Chinese stuff. This is top shelf, highly quality controlled stuff. So you're going to have to pay for it, and I understand the value, and I wanted to give that value to my prototype, so I use that. However, you can get away with a much, much cheaper setup if you were trying to do this at home. The one thing I suggest not skimping on is your gauges. I've used on my second prototype, Vishay micro measurement gauges. They provide a lot of information. They do a lot of calibration of their batch gauges. The other hand, my third prototype used an omega gauge, or sorry, 2 omega gauges. A lot cheaper. They seem to work very well, but we don't have the same amount of tracking information. So for what I'm doing, and even if it was a saleable product, the Omega ones are quite sufficient. The only reason I went to Omega is because they make a gauge that Vishay doesn't. And it's the shear gauge that has 4 gauges per carrier. Whereas Vishay makes one with 2 shear gauges per carrier, or a very large, physically too encumbrant gauge. Wouldn't fit into the hole. Alright, I'm going to show you how to install strain gauge. What I'm going to do is, I'm not actually going to use a real strain gauge. I'm going to actually use some dummy gauges. Now this is just a little pack, you'll be able to see them a little clearer. They're not electrically connected, so you can't measure resistance. However, they are great for practicing. I'll show you how to do some of the after testing, such as resistance to ground and just making sure that your bridge is properly set up. So the first thing you need to do is identify the area which you're going to install your strain gauge. I'm going to use my old V2 crank. This was the second version of my power meter. You can see the amplifier and A to D board, and then that was soldered to the microcontroller. This is the one that the cable had to actually snake through, so it wasn't a very good design. However, if you look closely here, you see the 4 wires running down to this area, and there's two grids right next to each other, and you can see these grids here are on a diagonal, so those are shear grids. So if I was to put a twisting moment on it, on the crank arm, if I was to twist like this, I would get shear here, and that's how V3 measures the drive side crank power. So the first thing you need to do is identify where you're going to actually put your strain gauge. Normally this would be done with some sort of alignment gauge. On circular objects, I've used paper alignment gauges to install multiple gauges at 90-degree intervals and to approximate alignment on opposite facings. On a curved surface, it's a little more difficult, and you can usually do this kind of by eyesight. However, some alignment marks are preferable. I'm not going to do that because there's many different techniques doing it, but suffice to say, once you've sanded your area and you have your alignment tool design, possibly a paper gauge, you can put it down and then mark using a graphite pencil or the backside of what's called a dental probe to scratch. Not specifically where the gauge is installed, just next to the gauge there's alignment marks. If you look at the catalog from Vishay or Omega, or HBM, you'll see those little alignment marks, and they're very good at helping you install your gauges. So the first thing you need to do is clear the area of any grease. So that's where this CSM2 degreaser usually comes in. You can use a variety of other degreasing agents. This one's, I'm not quite sure the exact composition. N-propyl bromide apparently is the active ingredient. You'll also notice that I'm using a stack of paper, and I'll be discarding them as I go. So sometimes this sprays a bit, but the easiest thing is to spray it on the direct area in question. So quite a lot comes out. Take your gauze pad and wipe in one direction. And I fold it over and wiping again. All right, so that area should be sufficiently degreased. It's not like this has been in heavy contact with any grease right now, but feel free to spray more, rub it down, and then wipe it away in one direction. Now we're going to go on to sanding. I mentioned 200, 400 grit sandpaper. Currently at home I have a 320 grit wet dry sandpaper and some 600 grit. So I'm going to be using those. But generally, if you look at your surface, you don't need to go past 400. If you get to a polished surface, it's likely that your strain gauge won't stick. So you need to take some conditioner. This is the phosphoric acid. It's very mild, and you'll see it's in contact with my skin, and you just wet the area and start sanding. You don't want the area to ever become dry. You want to make sure it remains wet at all times. So this might entail reapplying some conditioner. You can mask off the area. I suggest using a transparent tape. PCT2M tape is very good for this. The Shays training course kind of indicated an approximate number of strokes, and I'm going to say that's pretty good. So, taking your gauze pad, wipe in one direction. You can see it's getting nice. It's getting nice and shiny in this area, and I'm just putting that aside. All right, on to this is the 600 grit. You can see a slight tear. I kind of just rip it off, but I cut a bit here. So applying some more conditioner A. Now we're moving to the 600 grit. Because this is a much finer grit, and we've had a pretty decent starting area. Surfaces of these cranks are pretty clean. It's not a bad situation. You don't want to apply this to, say, a sanded painted surface. And what I mean is, you don't want to loosely sand your paint surface and not get down to bare metal. You want to be at the bare metal. The adhesion of your, the adhesion of the paint to the surface can greatly impact that, and you see this has come off. So we want to now neutralize the mild phosphoric acid. So we're going to flood the area, and again, this is very light ammonia water. You know, it's not very damaging to your skin. The difference here now is we want to scrub this area back and forth. And if you look at that kind of closely, you can see the discoloration. And that's what we want to remove. Is you need to just re-scrub that area. flooding it again with the neutralizer. And again, wiping away. So now our surface is generally prepped. Since I don't care about the other side, I can use the folded over surface. And I'm just going to put these aside in my garbage pile. We've got a bit of wetness here, so just take that away, lay that down there, remove this, and again put that in the garbage pile. So we need a nice clean surface. Unfortunately, I can't find my preparatory glass slide, but you can use generally a piece of plastic, or one of the other surfaces that's mentioned is on the fine spools tend to come in these plastic cases. So using the plastic, and actually I think it's going to be a little preferable. I'm going to take the wire out, and what you want to do is you want to apply the neutralizer, get another, oops. If they've touched something else, don't reuse them. You want to keep everything nice and perfectly. Let me just check that's in the view. So you want to kind of scrub the area, and notice how I'm placing my finger kind of at the back of the head, and you're just scrubbing back and forth. You want a nice clean area. All right. And again, wipe one direction with a sterile gauze pad. Or sorry, it's not sterile, it's just a gauze pad. So that's pretty clean. Now I'm going to cheat a little bit, because normally as these strain gauges come in packages that look something like this. So you remove that, and then you'll notice that the back area is exposed. The grid area on these are CEA gauges, are protected. When you grab, you want to grab not on the terminals if possible, but do not grab in the gauge area. You want to grab the back area here where there's no sensing arrangement. If you pinch in this area, you're going to damage your gauge. You're going to put it down and realize it's non-functional. If you do that, you're going to have to tear off the gauge and resand it, and resanding becomes difficult once you put down the glue line. And if you're working in a small precision area, it's very difficult. So these little guys, very simply, yeah, it's hard to see there, it's not refocusing. They have a couple of different fake sensing grids. They're not real grids. They have a large and a very small terminal. And on the small side, there's actually two sizes. The far ones are very, very small, and the mid ones are just small if you consider this large. There is larger solder terminals on some gauges. So what we want to do now, taking your adhesion tape, I've seen cheap tapes used. I've had better results using a proper strain gauge instrumentation tape. What it means is they formulated the glue, the glue line, or sorry, the adhesive on the back of the tape. They formulated this such that it doesn't affect the strain gauges. It's not going to tear off the protective coverings on the CEA gauges. So what I like to do is, since you don't want to use the area that's been exposed to the air, is to fold it back and then pull it off. You need a little bit of a strip. And then to start from behind and move ahead. rubbing out any air bubbles. Now, what you'll notice is it may not be perfectly aligned to the tape, but that's okay. So when you pull this up, you want to peel at a shallow angle. You can go one corner at a time, peeling at a shallow angle, and that means that the gauge will come with it. And then take your area, align it to your alignment mark. So if I had some alignment marks here, I might want to move this around. Once it's near it, put the back side down first and roll your thumb through. So you don't want any air bubbles. And then once you examine it and it looks good, you can move on. So the next part of the process is actually installing the gauge itself. So we've got it located. It's on the tape carrier. So again, at a shallow angle, peel it back and notice that it's coming up with the tape. All right, that's looking pretty good. All right, so now I'm going to use a M-Bond 200 Catalyst C. This is essentially the main ingredient is an isopropyl alcohol, and it looks like a dye. The dye tells you when it's dry, so you want to wipe off the excess. You really don't need much of this, and then using the wide amount starting at the base, wipe away. You don't want to get any on the tape down here because we're going to apply our glue line here, and when it dries it acts as an activator and causes the cyanoacrylate, essentially the super glue, to accelerate its drying in this area, and you don't want to build up glue here. You want to have the glue under the strain gauge. You don't want too much glue around the strain gauge. This isn't going to be a perfect installation, primarily because the rest of the area around isn't taped off, so there's going to be some bleed out as I push through the gauge, but it won't be significant, and we'll check the glue line afterwards. All right, that signifies that that should be dry with. So what we want to do now is we're going to take our glue, which is essentially a super glue, and I've seen this work with super glues off the shelf, commonly referred to as crazy glue. The big difference is that this stuff is going to be kind of quality assured, which will mean that it should set in the right amount of time. The glue line, if done properly, should be of good quality. It can still have pitfalls. So you want to take your gauze, and this is kind of an art, and I still don't have it down pat perfectly, but you essentially put down your bead line, line up your gauge, and push. Ooh, that's exactly not what you want to happen. Push it through, apply thumb pressure. I usually like to try and close up the bottle because this stuff sets quick and then can harden. So I'm applying light thumb pressure. On video, you can see my thumbnail turning a bit white. So that's how much you want to kind of apply pressure. You want to apply it evenly over the area. For long-term installations, or especially long-term dynamic installations, you will want to use something better than this, generally an epoxy. I've had very good long-term results. However, it's not recommended. There is air temperature two-part epoxies. They're much more expensive. And there's high temperature set two-part epoxies. Generally speaking, the high temperature set ones are considered more reliable, especially for installation for transducer purposes. They require a specific clamping pressure to get the glue lines correct. Too light and you end up with a thick squishy glue line and less consistent results. Too much pressure, you've squeezed out all your glue, and then you have a gauge that will come off. So with if you're going to use a cheaper glue line or a cheaper epoxy, well, it's sometimes called one part epoxy, but a cheaper super glue or cyanoacrylate, what you'll want to do is probably apply a little bit of pressure for a little bit longer, and then when you take that pressure off, to let it set for a little while. You don't want to leave it only a minute and then pull it back. It may take 3 or 4 times longer to set. Generally speaking, if it's installed and you can't get the edges up when you go around with a dental probe or the edge of your tweezers, then you should be in a good situation. All right, so I'm going to leave that for a little bit longer. That indicates installation time. And I'm going to prep some wire to solder on. All right, some tips and tricks when handling fine gauge wire. Keep this fine gauge wire in a box. If you've left it kicking around like this, you can get small bends in it, which can expose the copper wire underneath this enamel coating. If you do that and you put it down and it shorts out to ground, your strain gauge might work. It'll give erroneous results. It'll act like a huge antenna, giving you bad RF results. So you want a high quality enamel wire. This is 34 gauge, but what you want to make sure you're doing is you want to make sure that it's protected, that it's not kicking around in a toolbox or something, that there's some motor protection. So you want to take off a certain length. This is only going to be an arbitrary trial length, and then take that. You don't want to reuse a bend area. I just bent it again, so you just snip that off. So with these wires, you'll have both sides tinned. You're doing a direct instrumentation. I find for these a weaker pincing pressure on your tweezers helps it work much better. Also, I'm doing this at an incorrect angle. So I'm going to put a little bit more flux on for the other pad. And there we go. And so now we need to remove that rosin solvent. Or sorry, that flux with some rosin solvent. Now, instead of PC2T2M, you could have used masking tape, and if so, then you can wet that masking tape, and you can usually use the brush to get it back up. You want to make sure you get rid of all the flux. Again, steep angle for removing this. The flux should help, or the rosin solvent should help. And you're going to let it dry. Try not to touch it. CA gauges are a bit more resilient. This is kind of an open face. This one's also open face here. So you don't want to leave them exposed too much. This is the strain gauge equivalent of a multimeter. It's called a gauge installation tester. You can see these 1%, 5% buttons there. But it also has this mega ohm, and it actually, when it's in megs, you can 1K meg, so 1 giga ohm. This can read up to the 20 giga ohm range. One of the things that has been pointed out is a lot of multimeters to try and measure that may induce higher voltages or using some sort of step-up amplifier, and some of the older multimeters could just zap your gauges. So you have this grounding connector, and then you would pinch onto these. Since it's a dummy gauge, we won't get any resistance. You can measure out on these, but what you'd prefer is to have a bondable terminal and then a larger cable coming off, or to measure at your circuit board that they're soldered to. And you would just measure on those two terminals. You would do a check on your multimeter. First thing, actually, you check your battery, make sure your battery's good. And let me just put that in perspective. So you'd make sure your battery is good. So that's good. And then you do a resistance to ground. And what you're wanting here is this, the rosin solvent tends to be electrically conductive. You want it fully evaporating. You want the flux out of there. So when you measure resistance to ground, sometimes it'll be down here. It may just mean add more rosin solvent and wait for it to dry if you can see some flux in there. Or it might just be wait for the rosin solvent to actually dry. And then I find it's generally safe once you're at the 500 mega ohm or the giga ohm range. You're generally safe to then look at protecting your gauge. You also want to measure the 1 and the 5% ranges. So you want these wires to be the same length. You can get mismatches there. It'll just change the resistance, and then it'll give you a percentage off. Some of the more sophisticated instrumentation devices have shunt calibrations, which can correct for cable length. So assuming that we've checked it, we've got a good measure of resistance, say 350 ohms from our two terminals. We have a good resistance to ground. What do we want to do next? Well, we want to protect our gauge. So you have several different options to protect your strain gauge. The most common is the air dry polyurethane, M-Coat A. This is, like I say, an air drying polyurethane. It provides a basic protection. Its instructions: air dry 20 minutes, cure 6 to 7 days at positive 75 degrees Fahrenheit. You give this thing 20 minutes, the resistance is high enough, so long as you didn't goop it on. So you just want to apply a light layer. You can pre-mask this area off with tape. And one of the tricks is that if you're trying to run traces of wires and they're sticking up, just let it get tacky and then tap it down, and it'll generally hold your wires in place. And you might want to add another layer of M-Coat A. This is not a good. It's not good for protecting in harsher environments such as outdoors. Vichy has a whole section on selecting a proper coating, and there's several other things that you can test that works. Generally speaking, what you'd want to do is use something like this, but then do some sort of enclosure about your strain gauge. Generally, that's how Quark and SRM does theirs. So there's a lot of work into making sure that those are watertight areas. You take your gauge installation tester and you measure the resistance to ground. What you'll see generally is that it's decreased, but as the M code A sets, the resistance will increase. And once it's again kind of at 5 giga ohms, you're generally pretty safe to conduct your experiments, or in this case, to start putting together your power meter. You'll want to kind of snake these wires parallel to each other. You should spend some time planning out directions, how you're installing your strain gauges, and where you're installing and what's the safest area. This is not a safe area, but version 3's, as you've seen from the pictures and the videos, is behind the arm in a generally fairly safe area, or it's inside the crank tube, the torque tube, and that's generally a very safe area. So that kind of concludes how to install it. If you're ordering strain gauge supplies, especially from Vishay, ask about practice pads. Put them down on a similar piece of metal. It's generally good practice, and that's exactly what they're for. The big downside is if you've shorted them out, if you've burnt through the gauge, you won't know, whereas a real gauge you will. However, the cheapest real gauges you can get are somewhere in the vicinity of $10. Whereas, unless you have access to a university, universities tend to be able to get a student strain gauge, which is a lot cheaper, something in the order of $2 to $4 each. I think they have they have a bit wider tolerances, but once you calibrate them, because all of this is calibrated from raw signals, it tends not to matter then, because just because they're off a resistance a little bit higher or lower, just because they're off a little bit doesn't mean that they're not linear. They're still linear devices. So eventually this will be nice and tacky and we should be good to go. All right, on to the next bit.